Okay, this slide present a more realistic transient stability scenario for a power system during a transmission line fault. So under pre-fault conditions, two parallel transmission lines share the power transfer between the generator and the infinite bus, resulting in a lower equivalent reactance and higher electrical power outputs. And during the fault, the electrical power transfer becomes zero because the fault blocks effective power delivery. After the fault is clear, one of the transmission lines is disconnected by the circuit breakers, leaving only a single line in service. Consequently, the equivalent reactance increases the post-fault electrical power transfer capability decreases as shown by the new power angle equation. This example better represent practical power systems where protection systems isolate the faulted line and network configuration changes after fault clearance. Okay, this slide illustrate the power angle curves used in transient stability analysis based on the equal area criteria. So the blue curve represent the pre-fault electrical power, P pre-fault E, while the green curve represent the post-fault electrical power, P postponed. So during the fault, the electrical output power drops significantly, causing the mechanical input power, PM, to exceed the electrical power. As a result, the rotor accelerates and the power angle increases from delta 0 to the clearing angle, delta clear, creating the accelerating area A1. So after the fault is clear, the electrical power increases again according to the post-fault curve, producing the decelerating area A2. For the system to remain stable, the decelerating area must be equal to or greater than the accelerating area. The figure also shows the limiting angle, delta limiting, and the unstable equilibrium point, SAU, which defines the stability boundary of the system. Okay, in this example, um, we want to analyze the transient stability of single machine infinite bus power system during a fault condition. The generator is connected to the infinite bus through two parallel transmission lines, and the system parameters such as transient reactance, inertia constant, line reactance, and internal voltage are provided in per unit value. So before the fault, the electrical power transfer is determined by the power angle relationship, resulting in an initial rotor angle of 24.62 degree. After the fault is clear, the transfer reactance increases and initial rotor angle increases and reducing the maximum transfer power and shifting the operating point. Let me add a new student. Um, so using the equal area criterion, the critical clearing angle can be calculated as a 66.0 degree, and this is corresponding to a critical clearing time of approximately 152 milliseconds. So this result indicate the maximum allowable fault duration for the system to remain stable after disturbance removal. Okay, this Example, investigate the transient stability of a single machine infinite bus system subject to a fault occurring at the midpoint of the one transmission line. Here in this point, middle of the transmission line. Okay, the system consists of a generator connected to the infinite bus through two parallel transmission lines with identical reactance values, key machine and network parameters, including transient reactance, inertia constant, internal voltage and operating power are specified in per unit quantities. During the fault, the effective transfer reactance increases significantly, causing a reduction in electrical output power and accelerating the generator rotor. The analysis focuses on evaluating the system response and determining the stability limits after fault clearing using transient stability concepts and the equal area criterion. Okay, this slide illustrates the pre-fault, fault, and post-fault operating conditions of a single machine infinite bus system for transient stability analysis. In the pre-fault condition, the generator transfers power through two parallel transmission lines, providing a lower equivalent reactance and higher power transfer capability. During the fault, disturbance occurs at the midpoint of one transmission line, significantly increasing the system reactance and reducing the electrical power output. This causes the generator rotor to accelerate due to the imbalance between mechanical and electrical power. After fault clearing, the, the faulted line is disconnected and the system continues operating with only one transmission line in service, so resulting in a new post-fault power angle characteristics. So the equivalent reactance models shown on the right side are used to derive the power transfer equations for each operating condition and to evaluate system stability using the equal area criterion. Let me add a new student. No. Okay. This slide illustrates the fault analysis of a power system using the Thevenin equivalent method. The network inside the dash box is this is a blue dash box, is simplified by replacing it with an equivalent voltage source and impedance seen from the fault location. First, the equivalent reactance is calculated by combining the parallel reactances, resulting in X Thevenin is equal to um, 0.133 per unit. Then the Thevenin voltage is obtained using the voltage division principle, so everybody is about that one, right? If we know this voltage, we can simplify, find V Thevenin. And finally, the original system is reduced to a simpler equivalent circuit with a generator reactance J0.3 per unit in series with the Thevenin reactance, which makes the fault current calculation easier and more efficient. Okay, this slide presents the pre-fault, fault, and post-fault condition of transmission system during a fault event. In the pre-fault condition, the system operates normally with both transmission lines in service. During the fault condition, a short circuit occurs on one of the parallel lines and the network is simplified using the Thevenin equivalent to facilitate fault analysis. The equivalent reactance and voltage are represented as J X Thevenin is equal to J0133 per unit, and V Thevenin is equal to this value. So after the fault is clear, the faulty line is disconnected by the circuit breakers and leaving only one transmission line in operation. Let me. And this post-fault configuration changes the system reactance and affects the power transfer capability and system stability. This slide shows the electrical power equations of the system during the pre-fault, fault, and post-fault operating conditions. The power angle relationship is expressed as a function of the rotor angle delta, where the transmitted electrical power depends on the equivalent reactance of the network. In the pre-fault condition, both transmission lines are connected, resulting in lower reactance and higher power transfer capability. During the fault, the Thevenin equivalent network is used, increasing the effective reactance and significantly reducing the transmitted power. After the fault is clear and one line is disconnected, the system operates with a higher reactance than the pre-fault case, causing a reduction in the maximum transferable power. These equations are essential for transient stability analysis and evaluating the rotor angle behavior during the disturbances. This slide illustrates the application of the equal area criterion for transient stability analysis in a power system. The pre-fault, fault, and post-fault electrical power curves are shown to explain the rotor angle behavior during and after a disturbance. Area A1 represents the accelerating energy gained by the generator during the fault condition, while area A2 represents the decelerating energy after fault clearing. For the system to remain stable, these two areas must satisfy the equal area condition. Otherwise, they cannot be a stable system. So the figure also highlights important operating angles such as the initial rotor angle, clearing angle, and maximum permissible angle, which are essential for determining system stability and the stability limit after faults. So this slide also represents the mathematical application of the equal area criterion to determine the critical clearing angle for transient stability analysis. The accelerating area A1 during the fault condition is equated to the decelerating area A2 after fault clearing to maintain system stability. The slide shows the integral formulation of the criterion using the fault and post-fault electrical power equations. By substituting the corresponding power angle expressions and solving the equation, the critical clearing angle can be obtained as um, this value. Delta critical is equal to 100 degree. So this value represents the maximum allowable rotor angle at fault clearing for the system to remain stable. Otherwise, it will be unstable. Okay, this slide explains the main factors that influence transient stability in a power system using the equal area criterion. System stability can be improved by reducing the accelerating area A1 during the fault and increasing the decelerating area A2 after the fault is clear. Smaller A1 means the generator gains less kinetic energy during the disturbance, while the larger A2 allows the system to absorb more energy and restore synchronism. Factors such as faster fault clearing, stronger transmission networks improve post-fault power transfer capability, and reduce fault severity all contribute to enhancing system stability. Okay, this slide illustrates the main factors that influence transient stability in a power system using the equal area criterion. During a fault, the electrical output power decreases, causing the rotor angle delta to accelerate and increasing the accelerating energy area A1. So after fault clearing, the system follows the post-fault power curve where the decelerating area A2 helps restore stability. Faster protective relays and circuit breakers improve stability by reducing the fault clearing time and decreasing the clearing angle delta clear. So this increases the stability margin and allows the system to withstand larger disturbances. However, the practical limitation is then that extinguishing the arc in circuit breakers cannot be done instantaneously. So let me add a new student. Okay, this slide explains the effect of the system current inertia on transient stability. Higher generator inertia shows down the rotor acceleration during the disturbance, which reduces the increase in rotor angle during the fall period and improves system stability. As a result, the critical clearing angle margin becomes larger, giving protection systems more time to isolate fault safety. So, however, increasing inertia by adding heavier rotating masses is expensive and inefficient. In modern power systems, inverter-based renewable sources such as wind and solar do not naturally provide mechanical inertia, which creates new stability challenges for maintaining a reliable system operation. This slide shows how reducing the mechanical input power PM and electrical output power PE can improve transient stability. Lower power transfer reduces the initial rotor angle, it means delta zero, which increases SU, increases the availability stability margin, and allows the system to better tolerate disturbances. In terms of equal area criterion, the decelerating area becomes larger relative to the accelerating area, so improving the chance of maintaining synchronism after a fault. However, this approach has economic limitations because it may require reducing generation from cheaper power plants and increasing production from more expensive generating units. So this slide explains the main factors that affect transient stability in a power system using the equal area criterion. The curves represent the electrical power before the fault, during the fault, and after fault clearing. By reducing the transfer reactance X in the pre-fault and post-fault conditions, the maximum electrical power transfer increases. As a result, the initial rotor angle delta zero decreases and the stability limit SU increases, which improves system stability. The accelerating area A1 becomes smaller while the decelerating area A2 becomes larger, so allowing the generator to remain synchronized after this disturbance. So this demonstrates how network reactance and fault clearing conditions strongly influence transient stability performance. Okay, this slide discuss practical methods for improving power system stability. One important approach is limiting the pre-fault power injected by generators, since lower operating power reduces the rotor angle and increases the stability margin during disturbances. The allowable generation level depends on system operating conditions, including the transmission lines in service and the availability of other generators in the network. However, reducing generator output can increases the overall cost of power production. So therefore, power systems should be carefully designed so that generators can normally operate at their rated power while still maintaining adequate stability and security margins. Okay, this slide explains that reducing the reactance between generation and load is an effective way to improve transient stability. However, lower reactance increases the maximum transferable electrical power and strengthens the condition between generators and the network. This can be achieved by locating generation closer to load centers, constructing parallel transmission lines or additional transmission paths, and using higher voltage transmission lines. So since the base impedance in the per unit system is proportional to the square of the voltage, increasing the voltage level significantly reduces the per unit impedance. And another important technique is series compensation, which decreases the effective line reactance and further enhances power transfer capability and system stability. This is one of your questions for as a multi-choice question. So be careful. This slide is very important. Okay, this slide illustrate the concept of a series compensated transmission line. Transmission lines naturally contain resistance, inductance, and shunt susceptance, which influence power transfer capability and system stability. In series compensation, capacitors are inserted in series with the transmission lines to offset part of the line inductive reactance. This reduces the effective reactance of the line, increases the maximum transferable power, and improves transient stability. As a result, generators can maintain synchronism more easily after disturbance, while the transmission system operates more efficiently with enhanced power transfer capability. Okay, this slide shows a practical series compensation equipment and used in high voltage power system. This installation contain large series capacitors and protection devices that are connected in series with transmission lines to reduce the line reactance. By lowering the effective reactance, the system can transfer more power over long distances while improving voltage regulation and transient stability. Series compensation equipment is especially important in heavily loaded transmission networks where maintaining synchronism and increasing transmission efficiency and are critical for reliable system operation. This is a video you can have a look later. Okay, this slide highlights the challenges associated with series and compensation in transmission systems. Although series compensation improves power transfer and stability, it also creates protection difficulties because fault current and system behavior become more complex. Another major issue is the risk of synchronous response, uh, which occurs due to the interaction between the line inductance and series capacitor, forming an LC resonance circuit. If the resonance frequency matches the natural um, torsional frequency of turbo generator shaft system, dangerous mechanical oscillations can develop. So these oscillations may cause severe metal fatage, shaft damage, and even generator failure, making careful system design and protection essential. This slide introduces high voltage DC transmission as an effective solution for long distance power transfer. Unlike AC systems, DC transmission does not suffer from transient stability limitations caused by rotor angle dynamics. The transmitted power can be precisely controlled using power electronic converters, allowing fast and flexible operation of the system. HVDC transmission is therefore highly suitable for transferring large amounts of electrical power over very long distances with lower losses, improve controllability, and enhance overall system stability. This slide illustrates the existing and planned HVDC transmission lines across North America. The blue lines represent currently operating HVDC links, while the red lines indicate proposed future projects. Existing HVDC systems are mainly used for long distance bulk power transmission and interconnection between different AC networks. So the proposed projects aim to enhance grid reliability, integrate large-scale renewable energy resources, and improve power transfer capability between regions. So HVDC technology offers important advantages such as lower transmission losses, better controllability, and efficient transmission over very long distances, making it a key solution for future modern power systems. Okay, this slide explains the need for transient stability analysis using time domain simulation in modern power system. This is another multi-choice question. So although the equal area criterion provide useful insight into the factors affecting system stability, it is limited to simple systems and may produce inaccurate results for complex networks. Therefore, a more rigorous approach is required. Time domain simulation offers higher accuracy by numerically integrating the system differential equations and can effectively analyze multi-machine power systems under transient disturbances such as fault, switching events, and sudden load changes. So this slide introduces the concept of a differential equation which describes how a system state changes over time. The equation relates the derivative of the state variable xt to a function fx together with an initial condition x0 is equal to x0. So starting from the known initial value, the objective is to determine the trajectory of xt for all future time. Differential equations are fundamental to in power system dynamic analysis because they mathematically represent the behavior of generators, motors, and other dynamic components during the transient conditions. So this slide explains the basic idea of numerical integration for solving differential equations, starting from the initial condition x0 is equal to x0, as you can see. So the derivative of the state variable can be calculated using the function of fx if x0, so sorry, this one. So if we can derive xt, and the derivative represents the slope or tangent tangent of this angle. And by knowing this slope, we can estimate how the variable xt changes over a small time interval. Numerical integration methods repeatedly apply this process step by step to approximate the complex system response over time, which is essential in transient stability simulations of power systems. So this slide explains the basic concept of numerical integration for solving differential equations. For a very small time step, delta t, very small time step, the nonlinear function can be approximated by its tangent line at the initial point x0. So we can find f of x0 using the slope of function represented by dxt over dt at t time is equal to 0. We can find the f of x0. The next value of the state variable can be estimated as x of 1 is equal to x0 plus f of x times the delta t. So this approach is the foundation of the Euler numerical integration method, where the system response is calculated step by step over time using small intervals. Okay, this slide illustrates the step-by-step numerical integration process using a Euler formula. The continuous function xt is approximated by a sequence of small linear segments over each time interval delta t, starting from the initial value x0. The next values are calculated iteratively using the slope function f of x k. The general Euler update equation is x k plus 1 is equal to x k plus f x k times delta t. This method provides a simple and efficient way to estimate the dynamic behavior of the system over time by repeatedly advancing the solution in small steps. Okay, this slide presents an example of applying Euler numerical integration method to solve the differential equation dxt over dt is equal to 2x, x0 is equal to 1, using a small time step of delta t is equal to 0.01. The analytical solution of the system is given by xt is equal to Neperian number power 2t, and is compared with the numerical results obtained from Euler method. So the table here shows how the estimated values xk closely follow the exact solution at the beginning, but the numerical error gradually increases as the integration progress. This example demonstrates both the simplicity and the accumulated approximation error of Euler method. So this slide highlights the main limitation of Euler numerical integration method. To achieve accurate result, the time step delta t must be chosen very small so that the numerical approximation remains close to the actual solution. Although the error at each individual step may be small, these errors accumulate over time and can lead to instability where the numerical solution significantly deviates from the true response. In addition, using smaller time steps increases the computational effort and solution time. Therefore, while Euler method is simple and easy to implement, it is generally less accurate and less stable compared to more advanced numerical integration techniques. This slide introduces several advanced numerical integration methods that improve the accuracy and stability of the basic Euler approach. Higher order methods use information from multiple previous steps to obtain more precise results. predictor corrector methods further improve accuracy by first predicting the next value and then correcting it using a refined estimate of the derivative as in the modified Euler method. So variable step size method dynamically adjust the time step according to system behavior, and smaller steps are used during rapid changes while larger steps are applied during slower variations. Let me add a new person. Um, these techniques provide better numerical performance and computational efficiency for solving dynamic system equation. This slide also is one of your multi-choice questions. So this slide present the numerical integration of the swing equation using Euler method. First, Euler formula is introduced as a simple technique for solving differential equations step by step over small time intervals. Then the swing equation is converted into two first order differential equations representing the rotor angle and rotor speed dynamics. By applying Euler method, the continuous equations are transferred into discrete update equations for delta and omega, which can be solved iteratively at each time and step. Finally, the initial operating conditions are defined where the generator starts in steady state equilibrium with mechanical power equal to electrical power output. Okay, this slide explains the numerical integration of the swing equation under pre-fault operation conditions. Before the disturbance occurs, the electrical power output is equal to the mechanical input power, meaning the system is in a steady state equilibrium. As a result, the accelerating power becomes zero, causing the rotor speed to remain constant at the synchronous speed. Consequently, the rotor angle also remains unchanged during each integration step. This confirms that the generator operates steadily before the fault without any acceleration or oscillation. This slide describes the numerical integration of the swing equation during the fault condition. When a fault occurs, the electrical output power decreases and becomes smaller than the mechanical input power. So this creates positive accelerating power, which causes the rotor speed to increases above synchronous speed. As the rotor accelerates, the rotor angle also increases over time according to the numerical integration process. Therefore, both speed and angle grow during the fault period, indicating the generator is losing synchronism stability if the fault is not cleared quickly. Okay, I wanna close my session up to here because it's too much. And next week